Welcome back, students, to Organic Chemistry video notes. In this video, we're going to look at reading energy diagrams. So an energy diagram is describing the pathway with respect to energy when you're considering the progress of a reaction. So down here on the x-axis is going to be the reaction progress. Sometimes people call this the reaction, where reaction is abbreviated RXN, reaction coordinate. And it doesn't really matter what you call it, whether it's reaction progress or reaction coordinate. What matters is that we're starting here, so this is the starting point, and this is the ending point. And at the starting point are where your reactants are, and at the ending point is where your products are. And off to the side over here can be free energy, which is delta G, but you could also have something like enthalpy, right? You could have delta H there as well. When we look at these energy diagrams, we might see the potential for two different pathways. So here's one pathway where I'm showing A and B are my starting materials, and down here C and D are my final products. Over here I have the same starting materials, A and B, but we're going on a different path, which leads us to different products. Now notice how this pathway has this energy maxima here, right? That's called your transition state. Your transition states are where your bonds are breaking and forming at the same time. Now if your temperature is low, that means that you're not going to have a whole lot of energy to get over the hump, right? And this hump, the difference between the energy of that transition state and the energy of your starting material, that has a name. It's called energy of activation, or activation energy, and we abbreviate it E sub A. So if your temperature is low, then you only have enough energy to get over this smaller energy of activation. Whereas if your temperature is high, we have enough energy to get over the bigger hump. I like to think about this as like biking up a hill, right? If we're looking at the temperature being low, we're trying to get over, this hill, because with low temperature, we have low energy. And with high temperature, we have high energy, so we can get over that bigger hill. So when the temperature is low, what we'll find is our E and F are our major products. And when the temperature is high, our C and D will be our major products. And it all depends upon how much energy there is to get over that hump, that energy of activation. Let's talk a little bit more about those transition states. So if you have an energy diagram or a reaction where you have more than one step, then you're going to have more than one hump. Right, so this and this are both showing transition states. These are where your energy maxima are. You can have more than one transition state. And these are where your bonds are breaking and forming. So let's pretend that if we had a structure like this and the chlorine left, so if the chlorine did this and went away, then as that chlorine is leaving, the bond between carbon and chlorine is breaking, and that would be your transition state. And we draw that by breaking that bond, and the dashed bond is saying this bond is breaking. And then transition states are always in brackets with this symbol off to the upper right, and that's called a double dagger. It looks like a telephone pole with wires to me, but it's called a double dagger. And so this transition state is showing that the carbon-chlorine bond is breaking by drawing that bond that's breaking as dashed. If there was also a bond that was forming, we would also draw that as dashed. So these energy maxima here, those are going to be your transition states. Remember, we said that here was your reactants, here's your products, or product, doesn't matter. So what's in the middle right here that I just highlighted in yellow? Well, let's look at that next. That little valley is called an intermediate. So when we say that intermediates are the energy minima, we're excluding the idea that reactants and products are going to be lower than the intermediates. We're talking about this upper part of the graph where we're above the energy of the reactants. So the intermediates are not really things you can isolate, right? Reactants and products are stable compounds that you can isolate. Intermediates are like stepping stones. So if you were imagining, back when you were a kid hopping from one rock to another rock to another rock to another rock, pretend that this rock is on land and this one is on land. So here you have a rock on land where you're pretty stable. You're hopping here. This would be your intermediate. And at the top of your hop is your transition state. Right? And then we can do that again. We can do another hop to another intermediate, and then we can do a hop to, again, someplace that we're stable on land. So your intermediates are the valleys between the transition states. Remember, the transition states are here and here. When we start looking at reactions in the future, we're going to start utilizing terms like carbocation intermediate. You already know that carbocations aren't stable enough for us to isolate, and so they make great intermediates. Your transition states will be things that we draw in some of the reactions as well. So we want to mentally prepare for those as we get ready to actually apply this information to reactions in the future. So what should we know? We want to be able to look at energy diagrams and know what the different parts of them are. We'll save the kinetic versus thermodynamic products for a greater discussion when we're in organic chemistry too. I definitely want you to be able to identify the location on the energy diagram of transition states and intermediates and know what the difference is between them. Thanks so much for your attention. This is Katoni signing out.